Hello, and welcome to the presentation of my paper, Fusion Point Pruning for Optimized 2D Object Detection with Radar Camera Fusion. My name is Lukas Staecker, and I work at Opel, which is part of the Stellantis Group, and in collaboration with the German Research Center for Artificial Intelligence. Let's motivate this paper. With Radar Camera Fusion, we can exploit synergies via the complementary features that these sensors provide. In particular, the radar is good in measuring an object's distance, radial velocity, as well as working in adverse conditions, while the camera is good in localizing an object's angles and classifying it. However, when trying to fuse radar and camera data, two main problems arise. First of all, the data is on different frames, the image frame versus the bird's eye view frame. So we need to ask ourselves how we can associate radar detections with image data. The second problem is that the data is on a different semantic level as well, with the raw RGB pixels versus the radar detection list. So we also need to ask ourselves when it's best to fuse radar and camera data in our processing pipeline. For both of these problems, we made advances in this paper, which I now want to present. Let's start with the first question on how to associate radar and camera data. Since we're dealing with the task of 2D object detection on the image plane, it is most common to project the radar detections onto the image plane as shown in this frame from the nuScenes dataset. The problem is that we do not have any height information for our radar detections. So we need to make an assumption, for example, that each radar detection lies on the ground plane. But this will also result in very sparse radar channels. As you can see here, only a couple of pixels are filled with radar detections, while the rest of the image is empty. One solution provided in the literature is to incorporate a fixed elevation uncertainty, where we assume a fixed height for all detections, resulting in these vertical lines. We decided to go one step further and also incorporate a Gaussian azimuth uncertainty measurement. We take the azimuth uncertainty from the radar sensor's technical datasheet and model a Gaussian uncertainty curve. We then take the density values and multiply them with the radar cross-section of each detection, resulting in a new, denser radar channel that is also richer in information. The second question is when to fuse radar and camera data in our neural network. In the literature, we can find many early, deep, and late fusion approaches with varying pros and cons. One work argues that it's best if the network can learn itself where the fusion should take place. So they design a special architecture based on a retina net, which is the green, red, and classification regression part shown here, and add an additional radar branch with max pool layers that process the radar channels that are created as we showed in the previous slide. Then they add multiple fusion points at all stages in the network by concatenating the radar features to the image features. The network can then learn to adjust its weights where the fusion should take place. The problem with this approach is that it converges slowly and is difficult to find a good optimum. So our solution is a new technique called fusion point pruning, which automatically identifies the best fusion points in an architecture like this. So we start with this architecture, train for several epochs, and then evaluate the importance of each fusion point by looking at the layer activation in the first layer after each fusion point. We iteratively eliminate the least effective fusion points until we're left with an ideal architecture. So in our case, this is just the two fusion points after the C2 and C3 block of the ResNet backbone. Let's conclude by looking at the results. We compare ourselves with two image-only baselines and two leading radar camera fusion algorithms. In terms of the weighted mean average precision, our approaches with the azimuth projection technique and also in combination with fusion point pruning outperform the other approaches, especially when we take a look at night scenes only, where the camera is less effective and we get a significant increase in performance with our radar fusion. Thank you very much for your interest, and these are my references.